Okay, now let's go to our lecture 18. The purpose of our 18 is quite simple. Up to now, we have developed a drift diffusion simulator. You have your own drift simulator. Everybody now has it, but you have applied only to a system at equilibrium. So that is one limitation. Although your programming was done for diffusion simulator, which can solve the nonlinear equation, nonlinear system. However, you have applied it only to equilibrium system. Simply, in lecture 18, you are going beyond equilibrium assumption. So now you will try to solve, for example, m plus and m plus structure with certain bias, for example, 0.5 volt. So you have high reductive region and high reductive region, and also you have just a low reductive region. And previously, your two terminals are grounded at same time, but now you are doing this one. The left contact, for example, is still grounded. And now you wanted to apply a certain voltage. You know this number because you set it. For example, 0.1 volt, 0.2 volt, anything you want. And now, since we have two different voltages applied to this system, there will be conflict. For example, what happens if we apply in this way, ground way, and this way? Then although electron density at this point is not changed, also from our assumption, electron density at this point does not change. It is just given by equilibrium electron density. Also equilibrium electron density. No change at all. But when we consider electrostatic potential, what happens? In the case of electrostatic potential, this is also equilibrium potential. And when you go to this point, then you will find that the boundary condition for electrostatic potential at this right contact is simply given by phi equal to phi at equilibrium plus what? Plus our applied bias voltage. Certainly, if you apply 0.1 volt to the right contact, then there will be the potential difference by amount of 0.1 volt. If you apply 0.2 volt, then you will have 0.2 volt difference across the system. So in that case, you will have a non-linear response. So you will get charge transport. But fortunately, all of your implementation up to now is quite general. So actually, you can do it without further modification. Your code is already general enough, so you can just apply it to non-equilibrium cases. So that is our goal today. And let's go to the next part. So this our achievement, this slide is just saying the same thing I have done up to now. We can now solve the drift diffusion equation. However, it has been tested only at equilibrium condition. So now we have sufficient tool sufficiently capable tool to tackle with non-equilibrium problems. So today's goal is apply our code to non-equilibrium cases, and the reason why we are solving this equation, the eventual goal or our ultimate goal is securing the IV characteristics. Calculate the current as a function of given voltage. We have spent a lot of time, many lecture sessions for that that purpose. So now we are getting our ultimate goal. So calculate the terminal current as a function of the voltage. That's it. So now we are quite close to our final goal. Okay, then let's go to the real implementation. So I think that everybody has own implementation. So this is simply based on my implementation, and here we have to consider bias voltage. Previously we have not considered bias voltage. It was assumed to be 0, but now we have to consider it. For example, let's consider this one, residue vector. This one has 2 times n, because you know we have Poisson equation and continuity equation. That's simple. And also, since we have 2n unknown variables, so Jacobian matrix should be also 2n times 2n. And what is it? Here, when you have a look at, so this residue vector 1, this is assigned to phi 1, I guess. And in this case, phi 1 equal to what? Summer voltage times log doping density. This is just equilibrium potential. That's it. And since this Jacobian 1, 1, here we have Jacobian 1, 1 is defined as residue 1, which is partial derivative with respect to phi 1, and you know that this R1 is simply given by phi 1 minus a certain number, so we can easily understand that becomes just 1.0. So that's the reason why we have 1.0 here. After that, you can see that some loops for position index starting from number 2 up to n minus 1, which is the right end of a bulk node. We just calculate, you know what, this is just Poisson equation. So Poisson equation is assigned to this way. If you have i's position, then that is assigned to 2 times ii minus 1. If you have, for example, ii equal to 1, then you will have number 1. And if you have number 2, that will give you number 3, and later 5 and 7, and up to what? Up to 2n minus 1. Of course, since we are learning from 2 to n minus 1, we will stop here to n minus 3. So you can easily understand this is touching, for example, phi 2 up to phi n minus 1. And finally here we have to consider phi n. This is the contact where we have applied non-zero bias voltage. In this case, although it looks quite similar with our previous residue 1, comma 1, but residue 2n minus 1, comma 1, just to have additional term. Here, you have it. So, this one minus V applied simply means that now your phi n equal to Vt log your doping density divided by Ni plus applied voltage. So this one really impose non-equilibrium condition to your system. Although you have non-zero term or additional term here, your Jacobian entry is not changed at all because this one is just regarded as a given constant. So when you take the partial derivative with respect to phi sub n, of course this one does not, this one means that v sub applied does not contribute to any term to the Jacobian entry. In this slide, we are just to have a look at the Poisson implementation of a Poisson equation and compared with the previous one, which is given as black colored. The only difference is this red colored one, which takes into account the applied voltage to the right contact. Of course, if we apply non-zero bias voltage to left contact, then we have to change our residue vector or one component. So I think that is the only thing we have to change for our code. I think that we are really going slowly because the reason why I'm going slowly in these days is this part is particularly important. So drift diffusion is actually at the center of computational microelectronics. So if you have not done your homework properly, then please have your time to cover this lecture material. So understanding this drift diffusion equation is, or succeeding to implement the drift diffusion equation is the central purpose of, or central goal of this entire semester. Okay, so then continuity equation, in the case of continuity equation, no change error, that's it, period. Okay, then our overall structure just looks like this, and please have a look at it. So let's start from this bias. This bias variable starts from number 0 and ends up at number 10. And here we have applied bias voltage in this way. Bias multiplied by certain step value. So when we start from bias equal to 0, in this case, what will happen? In this case, we have nothing. So we have just applied voltage equal to 0.0. We will have this condition. After that, we will have Jacobian and residue construction. Then where should we be? Where should we have the initial gas generation? So please note that this is drift diffusion simulator. So I mean that before entering into this part, you have to first learn your non-linear Poisson solver. By learning your non-linear Poisson solver, you will have already phi equilibrium and n equilibrium. We are now assuming that the existence of equilibrium solution. So before starting this loop, we have already correct values phi and n. So when we learn this Newton iteration at this time, at bias equal to 0, so applied voltage equal to 0, since we have already good phi and n, it can be done without much difficulties. So before learning the zero bias condition, we have to provide equilibrium solution that is provided by nonlinear Poisson solver. So in this first round, there is no problem to generate Jacobian matrix and residue. And in this case, in this bias equal to 0 case, everything will be perfect because we have the solution already. So residual vector will be just quite close to number 0. So quite close to number 0 within numerical error or within your previous convergence criterion. So since residue vector will be quite close to null vector, your update vector will be also quite close to null vector. So when you add your update vector to phi and when you add your update vector to electron, then you will have quite a small number. So in this first round for your bias 0 will be immediately satisfied. So up to now we have talked about the bias equal to 1 case. If we go to bias equal to 1, then what will happen? Now here phi and elect will be the solution of bias 0. And after this is over, then we will go to bias equal to 1 case, and now our applied voltage becomes, instead of 0.0, now it becomes 0.05 volt. Then there is no change in the initial gas. So up to now, phi and electron density, they are just equilibrium quantities. And let's go to the Newton loop. What will happen? In this case, we are starting from the equilibrium potential, equilibrium electron density, and we construct a Jacobian matrix and residue. Of course, this residue will have highly non-zero values at the Poisson equation. All other residue, for example this one or that one, will be satisfied because previously we had already made the solution. But when you go to this line, previously your solution satisfied this one because your V applied was 0, but now you have 0.05. Therefore, your residue, whose index is 2n minus 1, have a value of, instead of 0, you have minus 0.05. Let's go to the continuity equation. And continuity equation, you have certain values and they are all satisfied by this solution. So there is no non-zero term. So simply speaking, at the beginning of your bias equal to 1 case, everything will be just 0, and just the second last entry will be minus 0.05. Okay, that will be your residue vector. And when you take the update vector, certainly you will have huge update vector. Then that will make this Newton loop run again. Finally, let's consider the next case or other general case, like bias equal to 2. After successfully run this bias 1 case, now here you have a solution phi at applied bias voltage is just 0.05 and electron density with applied voltage of 0.05. Then you go to this loop and your bias voltage now becomes 2 and applied voltage now becomes 0.1 volt. Then there will be no change in this procedure. For example, when you go to this Jacobian and residue construction, okay, although you have not the perfect solution, all of your other residue vectors or components of your residue vector will be quite close to 0, and only the term related with this boundary condition of Poisson equation will be disturbed, and you will have, for example, this value. So I hope that in every time at the beginning of your Newton loop, you will have this non-zero residue vector that initiate, that kick off the Newton iteration for next bias condition. So that will be repeated. The solution of previous bias condition is used as the initial guess of next bias condition without any modification. So I think that that's it. So your modification on your code will be really minimized. So now you can do your homework without much difficulties. The only thing you have to consider is now you have to calculate terminal current I. How can you calculate I? What you have done is just to calculate electrostatic potential and electron density. Then how can you calculate the terminal current I from these solutions phi and electron density? You can easily understand this one. If you have certain terminal, and certain terminal usually has a form of certain surface. For example, let's think about your device and you have applied a certain bias voltage. Then electrons will move. Electrons will move according to this streamline. After that, it will be collected in this surface area. So if you are interested with the current, then how can you calculate the current? Now you have full knowledge on electrostatic potential at every point and electron density at every point. Then from this information, how can you calculate the current? So first of all, please understand or please accept this convention of terminal current, the direction of terminal current. Here the arrow direction is important. Terminal current is always in this lecture or electronics defined as incoming flux. So when current is flow into the device or any element, then that is regarded as positive current. And if you have a certain current flowing through it that way, escaping from your device, then terminal current should be regarded as just -1. So this is quite important convention in my opinion. So please accept it. So if you accept it, then we can write down in this way. Any current at certain terminal can be expressed as the surface integration of your electronic contribution, the electron current density, and hole contribution, hole current density, the surface integration of these two vectors over surface of the terminal. Simply speaking, we can get the terminal current by integrating our Jn and Jp over this area. However, when you just take this integration as shown here, then you will have outgoing flux. So we have to have incoming flux, so different sign. That's the reason why we have eventually have minus sign in front of it. So that's it. This is the way to calculate terminal current. So let's apply this definition or this expression to our one-dimensional structure. If we consider one-dimensional structure and right terminal, then things becomes really simplified. So although we have to, in general, perform surface integration, however, in this one-dimensional structure, there is no surface at all. So I mean that this is just one single node, the rightmost node, just to represent the surface itself, and we have area. So this is just a given number. So this integration now becomes just minus times Jn x directional Jn multiplied by our area. Of course, if we are considering bipolar devices, then we have to also add the contribution from hole current density. But in this case, since we are talking about unipolar device only in this example, then instead it is enough to calculate it. Then, so simply speaking, if you wanted to calculate the right contact terminal, then this is corresponding to your minus Jn multiplied by area. Yeah, that's it. So then how can you calculate this number? This is just given by your Jn, and which is at the rightmost position. So then where do you have it? So between your n minus 1th node and nth node, you define J sub n. So that value is taken here. So you will get the solution, or you will get the terminal current immediately. Okay, so practically that is quite tricky. So when you try to implement or evaluate the terminal current, sometimes you will fail to get the correct value. So don't be fooled by signs. So please keep in mind, every time you calculate the current, you have to keep the directional convention. the terminal current is always defined as incoming flux. So that is important convention. And in this one-dimensional case, you can take the current density which is closest to your interested contact and take that Jn value and multiply the area of your system. So then you will get the answer. Then I hope that you can easily expand it to more general cases like two-dimensional systems. Okay. Then let's finish our lecture with homework announcement. Of course, due is next Monday. You have 5 days, and simply just calculate the IV curve of long and short structures. So apply the bias voltage to your right contact, and for example, we have to specify area. Just to specify it as, for example, what value 1 square micrometer, or if you want, you can set it by 1 square centimeter, whatever. So please set any area value, then calculate the IV curve of both of long channel structure and short channel structure. Okay, so I hope that since we have spent plenty of time already on this code, then I hope that you can easily get the solution. Okay, so up to now we have spent quite a long time to discuss about drift diffusion solver. So we are quite close to end of this discussion, but we have still have the most important lectures across this semester. So the most interesting and fascinating and practically important part is still remaining. So that will be covered in the next Monday lecture. So please focus on that lecture. Okay, then see you next Monday. Bye.